Hey everyone, welcome to the brave new world of integral calculus. My name is Darshan and I'll be your guide as we go through the various aspects of integral calculus. There's some really cool math out there. So yeah, let's just go ahead and get right into it. So a car is moving at a constant velocity of 10 miles per hour, and I'd like you to quickly calculate the displacement after 10 hours. So just a quick example there, just to get us warmed up into the right state of mind. So see if we can do that in just a second here. So it's not a trick question. I'm not trying to pull a fast one on you. It's as basic as it looks. We know that our displacement, is equal to velocity times time, right? And so therefore, we can just say, all right, so our displacement is going to be, we're going at 10 miles per hour, right? So we have 10 miles per hour times 10 hours. The hours cancel out, so all we're really left with is a total of 100 miles. Right? Nothing complicated here, just multiplication. Right? Let's do another example. All right, let's try another example here with a few nuances. So we have a car moving at 10 miles per hour at constant velocity again for 5 hours, but now the car suddenly slows down, like you sort of just hit the brakes, and you suddenly slow down to going at only 2 miles per hour for another 5 hours. So again, this doesn't really happen usually because it usually takes some time to slow down, but we're just going to assume that we suddenly go from 10 to 2 miles per hour, just for the sake of the problem. And once again, I'm going to ask you, what's the total displacement in the 10-hour interval? Well, the formula is exactly the same. We're still going to use displacement equals velocity times time, except we're going to need to do that for each of these intervals because the velocity does change here, right? So our displacement this time is going to be, we're going to have 10 miles per hour times 5 hours, plus we're going to add on the extra displacement from this other interval here. So we have 2 miles times another 5 hours. Once again, the hours cancel out just like they did before. This comes out to 50. And then over here we have another 10. So in total, we have our displacement ends up being 60 miles. Again, nothing tricky there, same formula. The only difference is because our velocity switches at this 5-hour mark, we have to break it up into two separate pieces here. All right, so now what we're going to do is we're going to do this problem graphically, right? So I've plotted velocity as a function of time for each of the two situations we saw here on these graphs, right? So if we can imagine this to be velocity as a function of time, you can see we're going at a constant 10 miles per hour for this entire 10-hour interval. On this other graph, this represents the second situation we saw. So we're going at 10 miles per hour for 5 hours, and then suddenly we drop down to 5 miles per hour for the remaining 5 hours there. So now we could also try and solve this problem, right? We could say we want to find the total displacement. As it turns out, finding the total displacement graphically is the same thing as calculating what's called the area under the curve. Right? So if I wanted to calculate the total displacement, it's the same thing as me saying, what would this area here come out to? In other words, this area between my function and the x-axis. Right? So what would this area come out to? Right? Let's go ahead and find that. So that area, well, this is just a square, right? If you can see there's a square there. So it has a width of 2 and a height of 2. So we're just going to, that's a width of 10 and a height of 10. So our area is just going to be 10 times 10, which is 100. Right? We can do the same thing over here, right? We can find this area between the function and the x-axis, which would be, in this case, we could break it up into two separate pieces there. So we have that area and this area. two different areas. Right? So we can find this total area, which would be, we have a width of 5 and a height of 10, so we're going to have 5 times 10, plus here we have a width of 5 and a height of 2, so we have 5 times 2. Again, we get 50 plus 10, so this again comes out to 60. Notice how we got the exact same numbers as we did in the previous process when we were using rate times time, right? So this is sort of a graphical way we can go about solving this kind of problem, right? We have a graph of velocity as a function of time, right? In each case, we have velocity as a function of time. We can find the total displacement by finding the area under the curve, or the area between the graph of the function and the x-axis, right? So that's that. Now here's a more complicated example. So a car's velocity in miles per hour as a function of time in hours is given by v of t is equal to t squared over 5 plus 4. And now I'm going to ask you to calculate the total displacement after 10 hours, given you this function for velocity. Well, that's a lot harder now, right? Because it's not quite as simple as using just rate times time, because the velocity at each instant of time is different. So using rate times time doesn't quite work. Likewise, if we look at the graph of this function, again, that's not an easy thing to find the area under, right? So because I'd be finding this area down here, and that's a very weird shape, right? It's not rectangular, it's not triangular, it's not circular. That's a very weird shape to be dealing with. So that's a problem for me. So that's really the sort of sphere of problems that integral calculus deals with. Let's talk about that. So what is integral calculus about? So let's draw a parallel to differential calculus, which we talked about before. So in differential calculus, given some displacement, right, given a displacement function, we can find the velocity at each instant of time, right? This is the whole idea of an instantaneous rate of change is all about. Likewise, we could also find the slope of the tangent line at a point, right? Because again, this is not something we could do with just slope formula, so we needed our derivative to do both these things for us, right? Now in integral calculus, we have a similar kind of issue, right? So we had this situation where if velocity is different at each instant of time, we need to find displacement. So the first question that integral calculus answers for us is, given a velocity, right? Given velocity as a function of time, like we saw in the previous example, we want to find the displacement as a function of time. It can also just be a number for displacement, like we saw there from 0 to 10, or it can just be displacement as a function of time. You can do either of those. Another thing that we want to do is we want to find the area under the curve on some interval, right? So again, we saw with the previous slide there, we saw the situation where we wanted to find that area under that rather weird shape. And we also wanted to find a way to find the displacement even if the velocity is changing continuously at each instant of time. Now those are two problems we don't currently have the tools to solve, but that's really what integral calculus is going to be all about, right? It's sort of using some really creative ways to try and solve those problems. So that's what we'll be doing in the next couple of videos. In the next video, we'll do a little bit more digging, and we'll go over the logic of sort of how the integral comes about, and we'll start talking from there. So I hope to see you in the next video.
If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!